Well, good morning, everybody. Good morning. How was your weekend? Good. It was good? I did a first pass through your exams. So I hope you had a really good weekend. Doesn't look good, but I have to do the second pass, and often things are better then. So, but I'll let you know on Thursday, right? You all saw the announcement, you can cry on each other's shoulders, all that sort of stuff. So make sure that you do that. There's a camera in the corner, okay? But that's for me. I'm part of a faculty learning program. And this semester, they want us to submit videos of our lectures, specific moments in our lectures. So I'm just going to let that thing run. You don't have to worry about it. It's all for me, right? And it'll never go up online. It's all internal stuff. So I don't even need to get waivers. I checked. I was like, I think all my students sign waivers. They're like, no. They have no rights. Great. I said, what are my rights? They're like, well, technically, I can prevent anyone from videotaping anything that happens in class, but I can videotape anything that happens in class. It's really weird. This is like a public space where anybody can videotape, but the stuff I present, the stuff I say is protected by intellectual property rights. It's weird. I'm so glad I never became a lawyer. It was terrible. So we'll just pretend, we'll forget that that's there. So we're doing chapter 9 today, all one chapter, right? And so this is one of the places in a very action-packed semester that I choose to cut corners. I'm not going to hold you responsible for these two sections, okay, 9.8 and 9.9. We may get back to rocket propulsion later if we have time. But 2D collisions are just an extension of one-dimensional collisions. We're not going to do them in here. I'm not going to give you homework on them. Basically, if you know your way around a vector, coupled with the stuff I'm going to teach you today, you can do any two-dimensional collision. But what we want to give you today is another toolbox. So far we've done 3, right? We've done kinematics, we've done Newton's law, and we've done energy. So momentum is the 4th toolbox out of 5 we're going to give you this semester. And we're going to save the 5th one till the last 3 weeks of class. So really, this is your last new big structure in physics for a while. We're going to be doing hereafter is applications of all 4 of those toolboxes. So momentum. What kind of objects have lots of momentum? Trains. Why do trains have so much momentum? Yeah, they've got a lot of mass, right? And as long as the train is moving, it has momentum. And that's really one of the keys here, is that momentum is all about how much a mass is moving. As a matter of fact, when Newton was first thinking about his second law, he actually did not think of it in terms of acceleration, okay, the way that we write it in its modern sense. Instead, right, what he was thinking of, okay, was changes in motion, changes in the velocity, right? And this is where he kind of developed the calculus. But, you know, if we take these little deltas and we make them small d's, okay, and then we move that mass inside, well, what we've got now is what I like to think of as the first or true definition of Newton's second law, okay? Which is this idea that forces cause changes in motion. And if momentum is this idea to capture the quantity of motion, how much motion does an object have, the combination of its mass and how fast it's going, and then that changes in time, well, the only way that you can change the motion of an object is to have some sort of force going on. So, momentum as an idea, pretty straightforward. But we can also couple it together with this concept and idea of force and time to pull off some really cool things. We're going to, let me rearrange this just a little bit, okay, where we have our, did you notice that the vector signs are back? Yeah. And then maybe instead of little d, so we don't have to do this all instantaneously, right? Maybe we'll just talk about it in terms of big deltas, so we can talk about averages. The change in momentum of an object, final minus initial, is related to force and time. We call this change in momentum right here, we call this impulse. Now, I do want to apologize in advance for the somewhat PG-13 subject matter of today's lecture, because whenever we start talking about momentum, we need to talk about this idea of a collision. And what's the first thing you think of when you hear the word collision? Cars, trucks, accidents. So trains and cars. So with all due respect to people that have been the victim of a car accident, it's a very violent experience. It's not something I wish on anybody. I understand the pain and trauma that's associated with that. So even though today I may make light of that and talk about collisions, right, in sort of a jokey manner, I don't want you to feel like, I'm making light of what can be a very serious subject. But we're going to be talking about collisions and accidents. We're going to be talking about guns and bullets. It's a lot of kind of very violent imagery that goes along with this. I've tried to figure out how to do this with unicorns and ponies, but it just doesn't. My daughter got horrified one day when I just didn't want to do that. So let's dive into this. And I think this concept and idea of a collision, one of the things that physicists have such a hard time dealing with is the fact that we speak an entirely different language from the rest of the people, right? I mean, when we say the word collision, physicists are actually thinking of any interaction between objects. Anything. So the objects don't even have to come into contact with each other. How can you have an interaction where things aren't coming into contact with each other? Gravity, right? So in space flight, you have a concept where you can use a planet or the sun in order to gain extra velocity. It's called a slingshot maneuver, where a probe goes in one side, it goes around the sun and comes out the other with a lot more speed. That's a conservation of momentum, in effect a collision, a gravitational interaction that takes place between the sun and that probe. Now, the sun's got a lot of mass, the probe's got a little bit, so the probe's going to get a lot of momentum out of that. The sun isn't going to change hardly at all. But they did, in a sense, collide. Now, you don't want your probe slamming into the sun, right? That's not a good thing. But there was an interaction there, exchange of forces, momentum changed. That's a collision. I guess you could come up with sort of an idea of putting really super strong bumpers on cars, right? And then they could collide without touching. That's being silly, right? But you don't have to have objects touching in order for momentum and impulse changes to be taking place. All right, I need 2 volunteers, actually. People that are willing to have stuff thrown at them. Jag and George, come here. Yeah, you can change your mind, right? Come here. This is good, nice and tall. All right, so George is going to have to be taller.
Okay.
All right, so George, come over here. All right, so I want you guys to hold that blanket up. Yeah, you know what? Yeah, that'll work.
Oh, I don't like that.
Okay, so I have here an egg, right? And they've got a blanket, okay? So if I were to throw this egg into the wall without the blanket in front, what would happen? It goes flat, right? Okay. What I'm going to do is I'm going to throw it into the sheet here. What I need you to do is I need you to hold the bottom kind of up. You got to make it cup.
Yeah.
There we go. That way we're going to try and catch the egg here. And scoot this way and come forward just a bit, because I don't want it to hit the board as I throw it. I'm gonna give it a nice good overhand here in a second. OSHA is gonna be very mad at us. So here we go.
Oh.
All right. Yeah, now they can't see. All right. This is good. All right, Jaden. Okay. All right, hold it up.
Okay.
All right, so let's see how this works, right? Okay. Oh, we've got it recording, don't worry. Here we go. Woo! Right? No egg, breaky. Should I do it again?
Yeah. Yes.
That's 2 out of 3. Let's see if I can get more speed on it. I didn't like baseball when I did it in Little League. There we go, right? Okay, so let's give these two guys a hand. Drop sheet. Perfect, thank you. And just to show that that egg was real, right? So, no hard-boiled eggs. Did anybody leave this in left?
Yeah.
I was going to use that at first, but I decided we shouldn't do that. All right. So, what happened there? Okay? Why would throwing an egg into the board cause it to break, whereas throwing it into the sheet didn't? What was different? Let's assume I'm really good, okay? Yeah, let's just stop that sentence right there. Let's assume that I threw both of those eggs with exactly the same speed, okay? Which means that from the time I threw it to the time it came to a stop in the blanket, right? The change in momentum is the same. Remember that the change in momentum, final minus initial. So I'm going to have mv final minus mv initial. There's going to be force. Yeah, I probably should have put my vectors in there. Times time. So the v final is 0, right? And they start off with whatever initial speed they had. So in both cases, right? But what's obviously different about the two cases, where we have just the wall and then we have the blanket? Okay, so the time is definitely different. And which one would you say is bigger? The blanket. What are you trying to say there? As it comes in and hits, to go from whatever speed it has to 0, right? There's more time here, okay? But with the wall, the direct impact, right? Less time. I can spell. All right. What effect does that have then on the force? If the impulse is the same, the change in momentum is the same in both cases, but time, more time, we've got an equal sign there, don't we? So what does the force do to compensate? More time. Bigger time means less force. And a shorter time means more force. So, there's a connection between the amount of force that an object is going to experience and the time it takes to change that object's momentum. Did you know since about 1993, all cars have come from the dealership pre-broken? You kind of suspected this, didn't you? With your car. Seems like something's always breaking on it. What do I mean that all cars from the dealership come pre-broken? Huh? Ah, okay. So I learned to drive in a 1971 International Harvester Scout 2. Now, for those of you that don't know strange old automobiles, this thing was a tractor that they decided to put a Jeep frame on top of. Okay? So before there were Jeeps, there were these things. And the International Harvester Company now makes big rigs. Okay? They don't make cars anymore. But they decided they want to make this Jeep type thing. And so that's what they did. They took one of their tractors and they put a Jeep frame on it. So as a matter of fact, on the front of my Scout, I could pull the front grill off, and there was a power takeoff connection right there for farm equipment. It was made in an era when cars were built in Detroit out of solid hunks of metal. And they gave people chisels and hammers and said, go carve a car out of that chunk of steel. Like, you were driving one of these around, you owned the road. Like, you knew that if you hit anything, it lost. Right? You could run into something and a little bit of hammer work on the body, you were back to rice. That car wasn't going to go anywhere. Nowadays, what happens when you pull a car up and it just bumps into one of those little concrete bumpers in the parking lot? It totals the car, doesn't it? Right? Okay, it's like everything falls. The difference is that cars from back in the early days, when you had collisions, even at moderate speeds, 25, 30 miles an hour, there would be body bags. Nowadays, you have collisions on the highway 65, 70 miles an hour, okay? And what you've got is car parts strewn for like a quarter to half a mile. And yet people are sitting there on the side of the road on their cell phone calling their lawyers. Cars are a lot safer nowadays, right? And how is it that they are safer? Momentum is going to change. Has to change. But engineers have figured out how to buy more time. They do it by pre-stressing parts of the car, the crumple zones. There's parts of a car that are not necessary for protecting people. Can you name a part? The engine. And what about the trunk? You don't need those parts to protect people. They're nice for making the car go, and they're nice for carrying things around. But in a collision, those things are expendable. So they designed those parts of the cars to crumple, to increase the time it takes for the momentum to change. But something else they've added to cars to make them safer, to increase time. Not the seatbelt. Seatbelts have been there for a long time. You don't know this because all of your cars nowadays have them. ABS is just a way to keep control. The airbags. What are airbags for? Cookie pillow? They're there, not cushy pillows. Anybody who's ever had an airbag go off in their face knows. It feels like you've been punched. It does, okay? But it's a whole lot better than being hit by either the steering wheel or the front windshield. Okay? So, because basically what is an airbag? It's an explosive. It's a small explosive device sitting there in your steering wheel or the dashboard. Okay? And when it detects that there's a problem, it blows up. Literally, blows up. Okay? And the expanding gases in that explosive push that bag open before your body has a chance, right, to get to the steering wheel, and it increases the time it takes for your body to come to a stop. The more time, the less force that's applied to you in that collision. There's all kinds of other safety features in cars, but those are the ones that deal directly with impulse. Let's talk about guns for a second. Okay, so there's a difference between a pistol and a rifle. Okay, one of the main differences is that a rifle's muzzle velocity is much higher. Given an identical bullet size and the amount of gunpowder in the bullet, a rifle can fire that bullet much faster than a pistol can. Why? Do the two bullets have the same impulse? Final compared to initial? No, I just told you they didn't. Why don't they have the same impulse this time? Which one's going faster? The rifle's going faster. So the change in momentum for these two is not the same. This one has less change in momentum. This one has more change in momentum. What's the same? In the impulse force time relationship, what doesn't change? Force. The force is determined by the amount of gunpowder in the bullet. The expanding gases as you burn that gunpowder, that force is a constant in this example. What does the longer barrel of the rifle do? It gives it more time for the force to act. Shorter barrel, less time for the force to act. Longer barrel, more time for the force to act. And here, if we get more time means, same force, okay? These are kind of two different examples here, right? More time for that force to act means that the bullet will achieve a bigger change in momentum. So when you're thinking about the relationship between force, time, and momentum, try to identify the thing that's staying the same. Do we have identical changes in momentum between the two cases? Do we have the same force between the two cases? Do we have the same time between the two cases? Look for the thing that's staying constant, and then you'll know the relationship between the other two things. All right. One last thought experiment for you, okay? Do not try this one at home. Stand on your table and jump off. What do you do when you land? You jump off and you bend your knees. Why do you bend your knees? Shock absorbers, right? What do we mean by shock absorbers? What are we doing? We're increasing the time it takes for us to change our momentum. We had a given amount of momentum right before we hit the floor, and we're trying to bring it to 0. Now perform the same experiment. Don't do this at home, but this time land with your knees locked. That will break all of the bones in your legs. Okay? What's the difference again? Time, right? Change in momentum is the same. Jump off the same level table, right? Okay? Same speed right before you hit the ground, still going to 0. That impulse is the same. But with the legs locked, the time to stop is much shorter. And so the forces will be much higher. So high that the bones in your knee especially cannot withstand that amount of force. So, careful about that impulse. They can get you. What are these? You know, if you are sort of charitable and understanding, you might say that they are there to protect people, right? I mean, they're put in front of that pole, right? Okay, in the event that somebody decides to steer their car into the pole. The cynical part of me says that they're there to protect the pole. But what I did is I went and pulled some data, right, and made some assumptions. And I'm giving these barrels quite a bit of leeway here. Okay? I'm saying that without the barrels in place, an impact would take about half of a second. I'm talking about for everything to come to a stop. So for crumple zones to happen, airbags, all. Now the truth of the matter is it probably happens much faster than that. Okay? But what I did in case 2 is I extended the amount of time by 1 second. So we're going to look at a 1 second difference in a collision and see what kind of change, what kind of difference that elicits in our outcome. What's exactly the same in both of these cases? The momentum. And more specifically, the impulse, the change in momentum. So, what did I just do right here? What is that? What did I pull out? The mass. Mass is the same, right? Okay, before and after. So I just pulled it out because I don't want to keep typing it in my calculator. Right? So the mass of the car, 1,500 kilograms. Final velocity is 0. Initial velocity is 25 meters per second. And when I go ahead and I calculate all of that out, I got something that's not in my note. There it is. Okay. Negative 37,500. Is that right? Yeah, I can read. Kilogram meters per second. That is the unit, by the way, of momentum. It's just the mass times the velocity. Very easy to confuse with a Newton, which is a kilogram meter per second squared. Right? But there is no special name for that unit. It's simply a kilogram meter per second. So I think we have an opportunity here. We could call a kilogram meter per second a balo. I think that could catch on. What would it be if it was plural? Let's see, would that be balos or balonians? Maybe we should stick with kilograms meters per second. All right. What's the negative sign for? It's kind of a direction, isn't it? So I didn't draw the picture, but if the car is heading to the right and it slams into a wall, okay, what direction is the force on the object? What direction is the change in momentum? It's to the left.
Which negative are you talking about?
The negative on the 37,500. It comes out, right? It's sitting kind of right there in the difference, right? And it carries through, and it just sort of seems to be there the entire time. But you see when I wrote in the numbers, I wrote in a positive 25. 0 minus a positive 25. That, when I said positive 25, I basically said whatever direction the car's going, I'm calling positive. And yet I still get a negative out. That's because the change in momentum was opposite the direction the car was going. All right, so there's our momentum. That's going to be identical for both cases. So let's look at case number 1, right? So we want to solve, we've got this change in momentum, this force, and this time. We solve that for force. Okay, we're going to do negative 37,500 divided by half a second. And that's going to be, and I'm doing magnitudes now. Let's just drop all these signs. And that's going to be 75,000 newtons. If I did this, 37 and a half times 2. Is that right? Yeah, 75,000. All right. And then let's look at case 2. Exactly the same. Calculation, different number for the time, 37,500, all divided by 1.5 gives us 25,000 newtons. So the difference here is 50,000 newtons of force, which for those of us that don't know what a newton is 11,000 pounds of force. So, if you had to be in an accident and had the choice of experiencing an additional 11,000 pounds of force or not, hopefully you would choose not to experience that. That's a lot of force, right? Was that 5 tons, 5.5 tons of additional force? And that's by adding 1 second onto the amount of time it takes for things to come to a stop. So it's a big deal for safety and other places. You've heard the phrase maybe to roll with the punches. What does that mean? Go with the flow. Sometimes life throws things at you and you can like fight it, or sometimes it's easier to just kind of go with it for the duration and then sort it out later. In boxing, okay, to roll with a punch when somebody's coming in at your face with a right hook or something like that, and you don't have time to block, then to lessen the force of the impact as it comes in, what do? You roll back. What are you doing? You're increasing the time for the impact to take place. You don't see that right hook coming in and go, right? Okay? That doesn't work as well. So, whether it's in boxing or in life, right? Impulse momentum relationships are important. All right. We need to talk about conservation of momentum, and I realize I forgot something. I'll be right back. It'll take me 20 seconds. All right, what is this? Yeah, Newton's cradle. This is the most misunderstood office executive's desk toy in the universe, right? Because you can go in the CEO office of any CEO in America who's probably got one of these, right? Okay, what does it do? Well, it is Zen or meditative. I don't know, right? Okay. To me, this is just a perfect example of conservation of momentum. Momentum being a conserved quantity means what? It's transferable. Whatever you had before, you have to end with, right? So so all of these balls are the same mass. And if I take one of them out and I let go, so I've given it some energy, right? And this potential energy is going to change into kinetic energy. And if I send it in, right, then one goes in and one goes out. There's a whole series of collisions here, right? Okay, and momentum is conserved mostly. You can see the amplitude dying away, right? Where's the energy going? Sound and friction, imperfections in the balls, that sort of stuff. But ideally, one comes in, one goes out with the same momentum, right, coming and going out. What happens if I do two? Right? Momentum must be conserved. It's kind of interesting if you want to think about this and get back to me later. Why doesn't one go out with twice the speed? All right. So, 2 in means 2 out. Okay. Well, if momentum is conserved, what happens if I do 3? There's only 2 left. So, according to conservation of momentum, 3 in means 3 out. What happens if I do 4?
4 in.
4 in, 4 out. What happens if I do 5? It works. All right. So momentum is a conserved quantity. It must be in the universe. The universe, I mean, we really have no choice. We can't break that. However, in the case of a car collision or a piece of putty falling on the floor or anything like that, you have a situation where you have some momentum and then it goes to 0. And if you kind of narrowly look at what happens to the car, you're like, wow, we just broke conservation of momentum. Not true. Where did the momentum go? Into the wall, into the earth, right? There's always something else that's changing its momentum. But sometimes we do narrowly focus in on just 1 or 2 things, okay? And kind of dump momentum out into parts unknown. We are going to conceptualize our momentum conservation like this. And when we do have a situation where, it looks like there's maybe some inputs or some losses or stuff, we're just going to ignore those. At this level, we're just going to not worry about that, okay? But we are going to do those that we are going to talk about 2 broad categories of collisions. There's elastic collisions and there's inelastic collisions. An inelastic collision is basically what every collision is. An elastic collision is a perfect collision. They very rarely happen in our everyday experience because any collision that involves some loss of energy. Now, specifically, in mechanics, we talk about kinetic energy not being conserved. Now, in general, kinetic energy isn't conserved. You got potential energy and kinetic energy and work other. They're all trading energy with each other, right? But if we narrowly look at what's happening to the kinetic energy of an object, we find that in a perfect situation, then kinetic energy is conserved. However, in most instances, kinetic energy is not conserved. One of the kind of, if you're wondering whether you have an elastic or inelastic collision, always assume it's inelastic. Okay? It's just if you're not told anything. At this level, in the homework, in the book, on the test, we'll be kind of careful to say a perfectly inelastic or a perfectly elastic collision. I can do a perfectly elastic collision right now by throwing my keys into the air. As long as we're not talking about what my hand does, and we're only talking about what gravity does to my keys, then the entire time they're not in my hand, they're undergoing a perfectly elastic collision. In this case, the collision is the interaction with the gravitational field. The that's kind of hokey, right? That doesn't, it's like, well, that's not a collision. It didn't slam into something, right? So if I drop the keys onto the table, elastic or inelastic? That's inelastic. Because my kinetic energy before the interaction was high, and then after the interaction it was 0. Kinetic energy is not the same before and after. That was inelastic. Look for things like sound. Look for deformation. Look for objects sticking together. Those are keys, oh, pun intended, to understanding whether or not you have an inelastic collision or an elastic collision. Like I said, in Physics 4a, everywhere we tend to be careful with making sure you know. Now, there isn't that much else to teach you about conserving momentum and doing problems. We're going to approach it much the same way that we approached conservation of energy problems. However, because physics textbook authors can't help themselves, they have to make this harder than it really is. So, this is a feature of Physics 4a. This comes up quite often in real life, but just so you realize what's going on here, I'm going to show you kind of a scary slide. But I hope that this is going to make some sort of sense. I'm going to make sure to capture this one so it ends up on Dropbox for you. Okay? What I am teaching you, the new part of Chapter 9, is right here in the middle. Okay? It happens in a very short space of time. It happens as two objects are interacting with each other. Before those two objects ever interact, there's other things going on. Conservation of momentum only happens in those instances when things are pushing and pulling on each other. Before that, sky's the limit in terms of what's going on. We can use conservation of energy, we can use Newton's laws, we can use kinematics. After the impact, after the collision, again, can't use conservation of momentum anymore, we use conservation of energy, Newton's laws, kinematics. So this chapter is going to give you an opportunity to practice some of those other things. My advice is always start with energy, because energy is the most straightforward, right? So you could end up doing conservation of energy, conservation of momentum, and conservation of energy in one problem, breaking it up into 3 parts. It's just the nature of this subject. Okay? Sometimes it isn't. Sometimes it's just 2 parts, right? Very rarely is it just the middle part. So what I do, because the universe is sort of built this way and physics textbook authors have written it this way, what I tend to do is I start right in the middle. I start with, oh, okay, so things are impacting, there's conservation of momentum applies. I'm going to look at that part first, and that's going to tell me what I need to do before and after, right? It's going to help inform what's going on, rather than kind of blindly wade into it and then wonder what I'm doing. So basically what I've got from now on is a series of examples, okay? It's just, want to show you the pattern of setting up situations where you have conservation of momentum in play. One of those examples is called the ballistic pendulum. In the days before modern technology for measuring muzzle velocities of cannons and rifles and all that sorts of things, one way to do this was to actually fire a cannonball into a catcher. Another cannon that caught the projectile, and then that whole thing swung, okay? Just like a big pendulum that swung up. And by measuring how high that pendulum swung up before it came to a stop, you could work backwards to how fast the bowling ball was going, or the cannonball was going, as it came out of the cannon. So, let's set that up. And like every physics problem we've done so far in this semester, we start with a visualization. Some sort of way to organize what's going on. Now, when it comes to conservation of momentum, whenever there's a collision or an interaction going on, I like to draw sort of a before, during, and after picture. What do I mean by that? Well, we've got this pendulum, this catcher, right, that's hanging from its support, maybe a string. And then we've got this, I'll draw it as a bullet, okay? But we've got this bullet that's coming in And it's going to strike that pendulum. So this is the before, right? And then we've got the during, which is when the bullet embeds itself in the pendulum. And then we have, whoa, my pendulum's getting bigger. We have an after, okay, where the pendulum is swinging up, right? So the conservation of momentum part is only happening in that middle step, that during, okay? That's where the bullet and the pendulum are colliding and they're exchanging their momentum, all that sort of stuff. We want to know how fast the cannonball/bullet was going before. And so I'm going to start giving it some labels, okay? I'll call this V bullet initial. Okay? And then I guess technically I have a speed of the pendulum, but what's the speed of the pendulum initially? It's 0, right? Now, afterwards, this is kind of interesting, right? Because, I mean, does the bullet have a speed that's different than the pendulum speed? No, they're stuck together, aren't they? And so we can maybe think of this as a V, I'm just going to call it V final, right? It's kind of a combined object right there. So like I said, I like to start in the middle, right? I like to start with my during because during the collision, I need to be conserving my momenta. Before the collision, initially, what has momentum? The bullet, right? So I'm going to write that down. Mass of the bullet, V bullet initial. All right, and that's a vector. That's the only thing that has momentum, doesn't it? All right. After the collision, what has momentum? The bullet pendulum combination. So one way to write that would be mass of the bullet plus the mass of the pendulum, V final, where I've combined the two masses together. I do want to point out that you can continue to treat them separately. You could have mass of the bullet, V final, plus mass of the pendulum, V final, right? Still treat them as kind of two separate things. But since they have the same speed because they're attached, can you factor this V final out? And then you get exactly what I wrote on the screen, right? So it doesn't matter how you wish to think of the system. It works out either way. Pick which way is more comfortable for you. For me, it makes more sense to think of them as a combined object where their masses add together with a certain speed, which is why I write it like that. All right. We're solving for velocity of the bullet initial. So I take my mass of my bullet and I divide it to the other side. V final. Okay, so these vector signs are starting to make me angry. Can I drop them? Can I get rid of them right now? What is that trying to say in terms of direction? Whatever direction it has after the collision is the same direction it had before the collision. Isn't that what that's saying? There's no minus signs anywhere in here, right? So at this point, I think maybe I can just say, you know what, fine. Whatever that direction is, I'm going to call it positive. So I don't want to keep drawing vector signs on this thing, right? So I can go ahead and just sort of quaintly get rid of my vector signs and just say this is my positive direction, right? All right, but if I want to solve for the velocity of the bullet initially, I need to know how fast this thing is going after the collision. I need to know V final, and I really don't know what it is because they don't tell me. All they tell me is this height h. So how am I going to go find out how fast this thing is going after it collides? We've done the collision part. The collision part has given us this statement where I've got two unknowns. Velocity of the bullet, which I want to know, and the final velocity, which I don't know. This is where we have to reach out to our other toolboxes and try to figure out, is there something we've been given that we can use to work back to what that speed is? And the answer here is conservation of energy. They've given us a height that this pendulum swings up to, right? It goes up through a height h. So if I set a 0 point to be the low point of the pendulum, and I call for my conservation of energy an initial and final condition, I'm doing a separate problem now, then my work other plus energy initial equals energy final. Is there any friction as that pendulum swings up? Do they tell us anything about any friction in the pendulum? No, so we're going to assume it's frictionless. Is there friction between the bullet and the block as it embeds itself? Absolutely, right? But we don't have to worry about that friction because we're not doing that part of the problem. That part of the problem was handled how? Conservation of momentum. It's kind of nice. Hit all that stuff from us, right? But we don't have any friction in the after portion here. So initially, does the system have any energy? Right after those two things collide, is it moving? Yes. 1/2 m. And what speed is it? It's the v final we're looking for, isn't it? This is where things kind of get confusing. Because the final velocity in one part is like the initial velocity for another part. Okay? So whichever way you want to think of this, maybe I'll call v initial down here. Okay? And then what kind of energy does the pendulum have at the final point? It's just gravitational potential energy. What mass goes in here? Doesn't matter. It would be the combined mass, wouldn't it? Okay? The mass would be, the mass of the bullet plus the mass of the pendulum. But it cancels out anyway, so it doesn't matter. And this V initial turns out to be the square root of 2gh. But this V initial is really the V final for that part right there. Come up with a way that works for you to organize this information. Right? You could label things A, B, C, or 1, 2, 3, or whatever works for you, but do try to keep these things straight. Feeding one part into the next. We've seen this before in kinematics, where you have one acceleration, and then you got to take the final for the first part and make it the initial for the second part. So, shouldn't be too weird for you. And now I can write the velocity of the bullet as mass of the bullet plus mass of the pendulum, mass of the bullet, whatever that ratio is, and then square root of 2gh. And there it is. I can find out any bullet speed, any cannonball speed, if I can simply measure how high that pendulum swings. I know the mass of the ball, and I know the mass of the bullet. Not bad for the British, huh? One of the ways they became a world superpower. And then there was Brexit. Right. I know I'm going pretty fast today. It's because I am trying to get one chapter done in a day. We need time for the other chapters. By the way, your next test is 2 weeks from this Thursday. We only have 3 weeks for this unit. And the unit after that is also only 3 weeks long. First 2 units have been 4 weeks long. Right? So, yeah. Buckle up. Really taking the training wheels off now. All right. We did a problem back in chapter 4 with I think it was the car on the hill. The car rolled down the hill and off the cliff into the ocean. Okay? So we're bringing that motorist back. Maybe they live in San Francisco. But we've got this situation now where, no, I can do better than that. Let's use the straight line tool. We've got our hill. We've got our motorist. We've got a big truck down here, right? And this car is going to come along, and it's going to smash into the truck, right? And what are they asking us to find? They want us to find out how fast the truck is going after the collision and if there's any mechanical energy that's lost in the collision, okay? So what I would like you to do right now with each other is have a discussion about how you're going to set this problem up. In the sense of be overarching and talk about what are you going to use on either end of the instant where they come into contact, right? How are you going to figure out the information you need to know? Identify the information you don't know. How are you going to get there? Have that discussion right now. Don't worry about writing anything down. Go. Launch windows, you know. All right, what have you come up with? Let's do the dead giveaway. Conservation of momentum is happening right here, isn't it? Okay, so we know that. But what are we going to need to know before we can do that? Velocity of the car at the bottom of the hill. So how are you going to do that?
Using energy.
Oh, you're going to use energy conservation over here? Why not? Okay. Do we have everything we need to know for energy conservation? Yeah, they give me the height of the hill, right? So, seems like a dead giveaway. Okay, so setting that up, put 0 at the bottom of the hill, initial, final. Does anybody want to tell me what the answer is right now for how fast that car is going? Square root of 2gh. How do you know? There's no friction here, right? So, I start with gravitational potential energy. I end with kinetic energy. The mass cancels. The 2 multiplies. And then I take a square root. How many times does the square root of 2gh come up? A lot. It's the answer. When you don't know the answer to something, square root of 2gh. It works more than half the time. What's the answer to life, the universe, and everything? 42. Okay? But the answer to everything else is the square root of 2gh. Okay? And for those of you who don't understand the reference to 42, you need to start reading. So, this works for something that's falling. It works for something that's going down a hill where there's no friction, right? As long as there's no friction in your problem, as long as the initial or final speeds are 0, the answer is square root of 2gh. How fast it's going. So, it's kind of a handy shortcut to have in your back pocket. And don't be surprised if it keeps coming up, because it will. All right, so that's how fast it's going at the bottom of the hill. Right? What about our conservation of momentum part? Well, before the 2 cars come into contact, what has momentum? The parked car, right? Should we call the parked car mass number 1? And the truck mass number 2? Does that work for you? All right? So before we got M1, V1 initial. And it is a vector, so I'll keep it there for just now. And then afterwards, what has momentum? They both do. Right? Doesn't just stop. How do you know it doesn't just stop? Okay, there's that. But it also says the car rebounds and gives us the speed of the rebound. Are these objects connected to each other? No. So the car, mass 1, has a V1 final. And the truck, mass 2, now has its own final speed, before and after. I got to keep those separate. Now, I have some decisions to make. So, if I call V1 initial positive, moving to the right, the way I've drawn it in the diagram here, okay? Let's see, this V down here, we better calculate out what it is. Square root of 2G, and then 25 goes in there. Let's see, did I do that? Nope. Somewhere in here. Yep, 9 point, oh no, that's 5 meters per second. Why do I not have this in my notes? Anybody got this one in their calculator? What is it? 22.14. Do I hear a second? Yeah, okay. Meters per second. So if I up here put in my mass, 1,500 kilograms for the car. And I put in a positive 22.14. Then over here, this V final, V1 final, sorry, what do I put in for the number for V1 final? -5. Why do I put in a -5? It's going in the opposite direction. We're told it rebounds and goes backwards. And this is a vector quantity, so we've got to be really careful there, right? We're back to that minus sign that'll kill you. The 1 minus sign, right? That'll throw everything off if you don't carefully think about it. So before you drop those vector signs off, make sure that you have figured out, right, the directions for things. And then over here, I'm going to have 5,000 kilograms, V2. Fine, you can keep the vector sign over that one, or you can actually drop the vector sign on there as long as you don't make it positive or negative. Even if you know, like we know the truck is going to go which way. It's going to go positive, right? But even if you didn't know that, or if you knew it was going to go the negative direction, don't put a negative sign on it. Let conservation of momentum tell you what the directions are going to be, right? Just let it happen. All right, so we take 1,500 multiplied by 22.14, add on to that 5 times 1,500, and divide by 5,000, and we get our answer. It's going to be a positive answer, like we suspected. And when somebody gets the number, let me know. 8.14 meters per second. Thank you for being so fast on your calculators. My calculator's on the door taking videos. So it's positive, like we expected. Okay. Truck has momentum now. How would we calculate the mechanical energy lost during the collision? It is kind of work other in a sense, okay? But we can actually get at it more directly. We can just do the kinetic energy initially and the kinetic energy final. Initially, what has kinetic energy? Just the car, right? But afterwards, we have the car and the truck. I'm not going to do the calculation right now, But you will, if you put the numbers in, you will find that the amount of energy afterwards is less than the amount of kinetic energy the car had before the collision. Where did it go? Sound, breaking glass, bending of metal, all kinds of places.
Did we just focus on kinetic energy because
Yes.
that's what did over last
Yeah, because collisions, the difference between inelastic and elastic is all about kinetic energy. Okay, I won't drop numbers in there, so I didn't bring my notes for that one. Can't go quickly. But this second one will be less energy than this one. Even though it looks like, oh my gosh, the truck has so much more mass, right? And there's two terms there, and you're adding them together. Overall, it's still less energy than what the car had initially. All right. Those were inelastic collisions that we just did, those two examples. However, with elastic collisions, there is an extra wrinkle that's often thrown in. And that extra wrinkle comes down to the fact that kinetic energy is conserved in an elastic collision. And that means that the authors of physics textbooks get really devious and start giving you trouble. What do I mean by that? I want to show you some magic. Okay? And I'm afraid that the magic at first is going to really overwhelm you. So I would say don't worry about writing anything I'm about to do down for like the next 3 minutes. So I'm going to do a whole bunch of math. You're welcome to write it down if you want. It's going to be on Dropbox. It's going to be on YouTube. It's the part at the end that's really, really critical. Okay? But I want to show you where it's coming from so that you understand. If you turn to your book on the section for elastic collisions, I kid you not, I think you see 8 different equations for dealing with an elastic collision. And as far as I'm concerned, that's like 7 too many, right? It's just like, what? Because what's going on there is that they're deriving equations for like very specific things. I want to do one setup that handles all of the situations and then work from that position of power, right? If I have one solution for all the situations, then I can just make it fit for what I need it to do. So this is going to be using some physics, and we're going to go like this. The situation is one where we have objects on a collision course, okay? And then afterwards, they collide and they bounce off of each other, okay? So they're coming back out, something like that, okay? And we will leave things in their generic forms, but I'm also going to drop off a lot of vector signs with the caveat that you got to mind your vector signs. You got to pick a direction that's positive, and then when you put in a number that's going opposite your positive direction, you can insert that as a negative value. Okay? All right. So what do we got going on here? In an elastic collision, we have to conserve both the momentum and the kinetic energy. Both of those things have to be conserved. So what are we going to know? Or what are we going to be given? We're going to be given the masses, okay? And we're going to be given the initial speeds of both of those objects. What we're after, what we don't know, okay, are the final speeds of the two objects after the collision. And that's 2 unknowns. So 2 unknowns means we need 2 equations, and the 2 equations we're going to use are conservation of momentum and conservation of kinetic energy. So in its full generic form, V1 initial plus M2 V2 initial, conservation of energy, momentum, should look like mass 1 V1 final plus mass 2 V2. There we go. That covers everything. Now, what happens if maybe mass 2 isn't moving? What do I put in for its velocity? 0. What if mass 2 and mass 1 are moving in the same direction initially? Then what do I put in? What sign do I put in for both of their velocities? Positive, right? So as long as you're careful with your positive and negatives for your velocities, this handles any situation, whether they're coming at each other, same direction. It does not handle the situation where they're heading away from each other initially. There's no collision there, right? Right? Sure. All right. So I wrote it out in full. Covered everything right there. And then I have to do the same thing for the kinetic energy equation. 1/2 m1v1 initial squared plus 1/2 m2v2 initial squared equals 1/2 m1v1 final squared plus 1/2 m2v2. Ah! It's a lot of stuff, isn't it? Okay. What are we solving for? We want these final velocities. I can clean up the kinetic energy one a little bit. What can I clean up here? I can get rid of the halves, because there's a half in every term. Can I get rid of all the masses? No. Because they're all different. Yeah. All right. Normally, in order to survive this mathematical jungle, we could maybe don't do this. This is the wrong way. Maybe solve for V2, which would get me 3 terms, wouldn't it? It'd be term number 1 plus term number 2 plus term number 3 equals M2V2 final, and divide by M2, right? And now I've got V2 final. And where do I stick this thing? And I square it. What happens when you square something with 3 terms in it? Death. Death is what happens. You get 9 terms when you FOIL that out. That's 3. And then you do it with the middle one for 3, and you do the last one for 3. That's 9 terms. Mixed. Squares and not squares, and the jungle just ate you. Don't do it this way. This is the wrong way. It's the wrong method. We're going to clear it all off right now, because this is the way that madness lies. All right. We're going to do a math trick instead. Okay? And the math trick is at once brilliant and amazing. And it's going to use something you probably have forgotten from high school. But it's okay. I'm here for you. I am going to gather all of the mass terms onto their respective sides. I'm going to look at kinetic energy. I'm going to move all mass 1 over to one side and all mass 2 over to the other. What does that look like? M1v1 initial squared minus M1v1 final squared. And over here I'm going to have M2v2 final squared minus M2v2 initial squared. And now I can factor out those masses, right? All right. Oops, great. And then we are going to attempt to remember that the difference between 2 squared quantities can be written a very special way. The difference of the squares. This would be V1 initial minus V1 final times V1 initial plus V1 final. Does that ring a bell at all? Do you remember that little rule that you probably had to practice a lot when you were learning factoring or whatever it was you were learning back then? That is like the one exception of all that math that you learned that's actually useful. Coming back to Hans here. I can do the same thing over here. V2 minus V1. Those are both final things. I wrote an initial over there. Boy. V2 final. No, that wasn't initial. What am I doing? This one that's wrong. V1 V2 initial, there we go, V2 final plus V2. It's so easy to make these things all wrong. Okay, so what I've done there is I've managed to eliminate the squares, right? Over on this momentum equation, I can do the same thing. Take a little bit of a shortcut. I'm going to factor the m out at the same time I move everything around. V1 initial minus V1 final. And over here, we get an M2 V2 final minus V2 initial. So I did two algebra steps there. I moved the masses to their respective sides, and then I factored it out. All right. Now what I'm going to do is I'm going to take this entire equation and I'm going to divide it into that entire equation. This is a legitimate method for doing algebra, and it can pull off some really amazing tricks. Oftentimes when I'm lost in a foiling hellscape, I'll step back and go, you know what, there's probably a better way to do this, and the answer is divide. When you divide equations into equations, you divide the left-hand sides into the left-hand sides, right-hand sides into the right-hand sides. V1 initial minus V1 final equals M2 V2 final minus V2 initial. And can you see it? Yeah. Boom! Done! V1 initial plus V1 final equals V2 final plus V2 initial. Now, I choose to write this as V1 initial minus V2 initial equals V2 final minus V1 final, just to get all the initials on one side and all the finals on the other. And the thing in the box, that's what you need to write down and master. Don't worry about where it came from. I just kind of wanted to show you that there was something from your past life that was useful. And there's another way to do algebra that doesn't involve just blindly plugging things in. But in truth, when you are presented with an elastic collision, do not set it up like I did initially. Use the thing in the box. Right? That is one of the equations that you will use for an elastic collision. The other equation you will use is the conservation of energy statement. The two things in the boxes on this slide are what you will use for solving every elastic collision problem that you are given. Not just in this class, but like going forward. Okay? It works everywhere. And let me see if I can't show you that right here in just the last couple minutes that I have. We've got these two bowling balls. This is the project, right? And I'm going to call the one with 8 kilograms mass 1, the one with 10 kilograms I'm going to call mass 2. It's an elastic collision because they tell me, don't they? Perfectly elastic. So I am going to set this up as an M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. I'm going to write that down, and I'm going to use V1 initial minus V2 initial equals V2 final minus V1 final. Those are the two equations that were in the boxes from the last slide. If I call the speed of the 8 kilogram mass positive 5 meters per second, what do I have to put in for the 10 kilogram ball? Negative 2. All right, so that's 8 times 5 plus 10 times a negative 2 with an 8 V1 final plus a 10 V2 final. Over here, V1 initial, 5 minus a minus 2. Do you see what happened there? I've got to be careful with my directions. And then I've got V2 final minus V1 initial. Those two equations right there, now you substitute, right? Maybe, I don't know, I don't care. Solve this one for V2 final. That's going to be 7 plus V1 initial, isn't it? And then that goes in there. Solve for V1. When I did this, V1 turned out to be negative 2.78 meters per second. And V2 turned out to be 4.22 meters per second. What does that mean the direction for the 8 kilogram ball is? It bounced off and is going back to the left. What happened to the 10 kilogram ball? Bounced off, went to the right. But this is much easier algebra than that last screen, isn't it? So please, 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 write down your conservation of momentum in full, and then use this magical equation over here whenever you have an elastic situation. Don't use that for inelastic. It assumes conservation of kinetic energy, which is not true in an inelastic problem. You now can do all of your Chapter 9 homework, in theory. What starts on Wednesday? Chapter 10. Have a good day.